So for everyone listening, I want you to start by just visualizing something for a second. Picture a completely ordinary, flexible, maybe slightly translucent film of plastic. Exactly the kind of stuff you might see feeding into a 3D printer or maybe being used for those dissolvable surgical sutures. It looks totally unremarkable. But, and this is the wild part, inside this specific sheet of plastic, embedded directly in its molecular structure, is a hidden, totally dormant biological demolition crew.
Yeah, and that crew, it has one highly specific programmed assignment. I mean, they are designed to wait, completely inert, for years if they have to.
Right.
Just waiting until they receive a very precise environmental signal. And when that signal arrives, they wake up, coordinate their biological machinery, and literally consume the plastic from the inside out.
It's crazy.
It really is. They reduce the entire structure to a harmless molecular soup in just a matter of days.
Welcome to our deep dive. So our mission today is to explore this really groundbreaking publication from May of 2026 out of Innovation Toronto. It details a human and AI co-creation called the living plastic.
Wait.
Okay, let's unpack this because we are looking at the peer-reviewed research behind this, which was published in ACS Applied Polymer Materials by a team led by Zhuojun Dai at the Shenzhen Institutes of Advanced Technology.
Yeah, the Day team.
Exactly. And if you follow material science at all, the holy grail has always been a polymer that behaves perfectly while you need it, but completely disappears the second you don't. But looking at their methodology, what strikes me isn't just that they got it to degrade, it's the architectural approach. They didn't just tweak the chemistry to make it weaker, they built a Trojan horse.
They did. And it is a profound shift in materials engineering. I mean, for over a century, our whole industrial paradigm has basically equated quality with permanence. Right?
Yeah, we want things to last forever.
Exactly. We manipulated long-chain polymers specifically to resist environmental breakdown. Yeah. We wanted plastics to shrug off water, heat, biological attack. But the Dai team's work, it completely flipped that.
Right.
They're treating the polymer not as this final permanent artifact, but almost as a temporary storage medium for a biological process. It's the engineering of intentional programmed impermanence.
Which is such a wild concept. But so how exactly do you pack a biological demolition crew into a solid sheet of plastic? I mean, plastic extrusion involves insane heat and pressure, right? Yeah. If you just mix standard bacteria into a vat of melting plastic, you're basically just going to get a sterile sheet of plastic full of incinerated cellular debris.
Oh, absolutely. You'd completely destroy them.
Right.
And that is exactly why the foundation of this living plastic relies on a very specific organism, which is Bacillus subtilis.
Okay, wait, I recognize that name. Bacillus subtilis. That's just a really common soil bacterium, isn't it?
It is.
It's not some crazy extremophile dragged up from a deep-sea hydrothermal vent.
No, not at all. It's incredibly common. But the reason it's the workhorse here is because of its evolutionary survival mechanism.
Okay, how so?
Well, when Bacillus subtilis encounters extreme environmental stress, we're talking starvation, extreme heat, radiation.
Yeah.
It doesn't just die. It undergoes this radical asymmetrical cell division.
Oh, wow.
Yeah, the cell basically copies its chromosome, packs it into this heavily armored dehydrated core, and then surrounds it with a thick protective cortex and a super tough protein coat. So essentially, it becomes an endospore.
Oh, I see. So it basically puts itself into biological stasis.
Deep stasis, yeah. In that endospore state, its metabolism just drops to practically zero. It is biologically inert.
Wow.
And the incredible thing is, these spores can survive being boiled, they can survive harsh chemicals, and crucially for the Day team, they can survive the thermal extrusion process required to manufacture polycaprolactone, which is the specific plastic they used in this research.
So they just mix the spores right into the raw plastic.
Okay. Exactly. The spores are mixed into the polymer resin, the plastic gets melted and shaped, and the spores just, ride out the thermal stress. They become permanently locked inside the cooling plastic matrix.
Okay, so that completely solves the survival problem, but the biology itself is heavily modified, right?
Yeah,
because they didn't just dump wild soil bacteria into the plastic.
Right.
They engineered two entirely distinct strains of this bacterium to carry specific gene circuits. Let's break down the mechanics of what these two strains are actually doing when they wake up. Looking at strain 1, the research describes it as producing an enzyme that cuts the long polymer chains at random points.
Yes. So strain 1 produces what biochemists call an endoenzyme. To really understand the mechanism, you kind of have to picture the molecular structure of the plastic itself.
Okay.
Polycaprolactone is an aliphatic polyester, so it's made up of incredibly long, repeating chains of molecules held together by ester bonds. Imagine a really dense, tangled forest of chemical connections.
Like a huge interconnected web.
Exactly. Now, the enzyme produced by strain 1 acts as a highly specific pair of biochemical scissors. Because it's an endoenzyme, it's capable of attacking the internal ester bonds within those long chains.
Okay, so it cuts from the middle?
Right, it just wades right into that tangled forest and starts randomly cleaving the bonds right in the middle of the chains.
But wait, if it's just randomly attacking the backbone, severing the chains into thousands of shorter ones, aren't we basically just causing a structural collapse?
Yes.
I mean, the material loses its tensile strength and falls apart.
Yes.
But structurally, I mean, that sounds exactly like the definition of microplastics. We aren't really destroying the plastic, we're just shattering it into microscopic debris, right?
You're spot on. That is the fatal flaw of a single enzyme approach.
Oh, okay.
If you only deploy strain 1, you destroy the macrostructure of the device, sure, but you leave behind this toxic legacy of persistent microscopic fragments. You've essentially just built a microplastic factory.
Which is exactly what we're trying to avoid. Which brings us to strain number 2. The research says strain 2 produces a processive enzyme. How does that differ from the random scissors of strain 1?
So a processive enzyme, which is an exoenzyme in this case, operates on a totally different mechanical principle. It actually cannot attack the middle of a polymer chain.
Why not?
It physically just does not fit. The active site of the enzyme is shaped in a way that it experiences steric hindrance.
The steric hindrance.
Yeah, basically physical blockages. If it tries to bind to the middle of a continuous chain, it's blocked. It can't latch on. Instead, it must bind to a terminal end, so to broken edge of a chain.
Oh, I get it.
Yeah, and once it latches onto that exposed end, it physically walks down the chain, snipping off individual monomer units one by one. It dismantles the fragment unit by unit until there's literally nothing left but basic molecular building blocks.
Okay, wait. If strain 2 is so incredibly thorough-like, breaking everything down to the fundamental monomers, why do we even need strain 1 at all? Like, why not just embed strain 2, wake it up, and let it eat the whole sheet of plastic?
Well, because of that steric hindrance we just talked about.
Oh, right, because it can't cut the middle.
Exactly. If you deploy strain 2 into a pristine, intact sheet of plastic, it literally just bounces off. The polymer chains are too long, they're too continuous, and they're way too tightly packed. There are virtually no terminal ends for the process of enzyme to grab onto.
So it has no starting point.
Right. It requires an edge to start its work, and an intact polymer matrix just doesn't offer any.
Okay, looking at how these two operate together, it reminds me of trying to clear an old-growth forest.
Well, that's a good way to look at it.
Yeah, like, imagine if you send in a reckless lumberjack with a chainsaw that's strain 1. He just runs around chopping down massive trees completely at random. He deconstructs the forest canopy, but if he walks away, you're left with an absolute disaster zone.
Right, totally.
You have thousands of these massive hazardous logs just slowly rotting on the ground. That's your microplastic debris field.
Yeah, the lumberjack shatters the architecture but leaves all the debris.
Right. Now, strain 2 is like bringing in a highly specialized, top-of-the-line wood chipper. It will turn any piece of wood into the finest, most biodegradable sawdust imaginable. But a wood chipper has a narrow feeding chute, right?
Mm-hmm.
You physically cannot shove a 300-foot intact redwood into it. It's totally useless against the intact structure. You need the lumberjack to drop the tree and hack it into manageable logs, and then you need the wood chipper following right behind him, feeding those severed logs into the chute to ensure absolutely nothing large is left behind.
That is exactly it. The mechanical synergy of your analogy maps perfectly onto the biochemistry. What's fascinating here is how the Dai team engineered these two enzymes to operate in a tightly coupled biochemical cascade. The source material actually uses the specific phrasing that they complete each other.
Complete each other? I love that.
Yeah. Strain 1 acts as the vanguard, relentlessly cleaving the internal bonds and generating thousands of newly exposed terminal ends. And then strain 2 immediately utilizes those ends as docking stations. It binds to them and processively chews the fragments down to single monomers.
And because they're being deployed simultaneously from within the material, the cutter just opens the molecular doors and the chewer walks right through them.
Exactly.
So the result is 0 microplastic residue.
0. None at all. And this really redefines how we need to think about material degradation. Because for a long time, the industrial definition of degradable was incredibly loose.
Oh, for sure. Greenwashing, basically.
Right. If a plastic simply fell apart into invisible pieces, we often just slapped a green label on it and called it a day. But true biological degradation is about molecular disassembly. It is the complete return of a synthetic structure back to elemental building blocks that can actually be safely metabolized by the environment without leaving a toxic legacy.
It's a perfect closed-loop demolition system. But, okay, understanding how efficiently these microbes devour the polycaprolactone immediately raises this glaring mechanical contradiction for me.
What's that?
Well, we have these spores baked directly into the plastic matrix, right? If they are this efficient, why doesn't the plastic just start melting the day it comes off the assembly line? I mean, a sensor that digests itself while it's just sitting in a warehouse shipping box is a pretty useless piece of technology.
Oh, totally. And that is the core engineering hurdle they had to overcome. The biology is incredibly potent, so the control mechanism has to be absolute. The spores have to be kept in that state of deep stasis until the precise moment of intended destruction.
The research notes they can remain dormant for years, in principle. But how do you design an alarm clock for an organism that is fundamentally walled off from the world, encased in solid plastic? Like, what actually breaches the hull and wakes them up?
It's a brilliant piece of multi-factor authentication, really. The spores do not wake up simply because time passes. They require a highly specific, dual-signal environmental trigger. First, there must be physical surface erosion of the plastic itself.
Okay, so the polymer matrix has to be mechanically or chemically compromised just enough to allow fluid ingress.
Exactly. The fortress walls have to be breached. But, and this is key, surface erosion alone isn't enough. If you just scratch the plastic, the spores stay entirely dormant.
Oh, interesting.
The fluid that enters through that erosion must be a specific nutrient broth. And crucially, that broth must be heated to exactly 50 degrees Celsius.
Wait, both surface erosion and a 50 degrees Celsius nutrient bath.
Yes.
Let's look at the mechanism there. Why that specific temperature? Why 50 degrees?
So the 50-degree threshold acts as a targeted heat shock. In microbiology, a brief exposure to elevated temperatures is often required to destabilize that thick protein coat of an endospore. The heat shock physically alters the permeability of the spore, and that allows the highly specific germinants in the nutrient broth, particular amino acids and sugars, to reach the germinating receptors embedded deep in the spore's inner membrane.
Okay, so the heat unlocks the door and the nutrients physically turn the handle.
Yes. Beautifully put. When those specific receptors bind to the nutrients, it triggers an irreversible biochemical cascade. The spore dumps its protective dipicolinic acid, rehydrates its core, and rapidly transitions back into a vegetative, metabolically active bacterium.
And then it's game over for the plastic.
Pretty much. At that point, the engineered gene circuits fire up, the plasmids begin transcribing those two enzymes, and the demolition begins. And the research shows that once this specific dual-trigger activation occurs, the entire polycaprolactone matrix is completely reduced to molecular building blocks within exactly 6 days.
6 days. From a solid electronic substrate to just a puddle of monomers.
Yep.
And the Dai team actually proved this outside of a petri dish, didn't they? They built a functioning, wearable medical device to test the real-world viability of this living plastic.
They did. They fabricated a flexible electromyography sensor, an EMG device. It's used to measure the electrical activity produced by skeletal muscles.
Right, like those patches they stick on you at the physical therapist?
Exactly. They printed highly conductive silver traces directly onto a substrate made of this spore-embedded living plastic. They attached it to a human arm, and the device performed flawlessly. It flexed with the epidermis, the electrical resistance remained completely stable, and it accurately read the muscle signals. The plastic behaved exactly like reliable inert plastic.
But okay, let's look at the practical reality of wearing a medical device. Let's say I have this sensor stuck to my bicep, right? And I go out for a 10-mile run on a blazing hot July afternoon. My body temperature is elevated, and I am sweating profusely. Sweat is a fluid containing minerals, salts, trace amino acids. So is my own sweat, combined with my body heat, going to inadvertently trigger the biological demolition crew? Like, does my medical device just melt into a sludge on my arm while I'm jogging?
It is a vital question for any wearable tech, absolutely. But when we analyze the biochemistry of the trigger, it shows exactly why that won't happen. The control systems are mathematically distinct from normal human environmental conditions.
Okay, lay it out for me.
First, consider the thermal trigger. The human body operates around 37 degrees Celsius. Even during extreme exertion, your skin temperature rarely exceeds maybe 35 or 36 degrees.
Right.
The heat shock required to destabilize the spore coat is 50 degrees Celsius. That is 122 degrees Fahrenheit.
Oh, wow.
Yeah. If your skin reaches 50 degrees Celsius, you are sustaining severe thermal burns.
Okay, so the thermal lock remains completely secure during human use. What about the chemical lock? Does sweat do anything?
No, because human sweat is primarily just water, sodium, chloride, and potassium. It does not contain the concentrated, highly specific blend of germinants like specific L-alanine amino acids that are required to bind to the spore's receptors and initiate rehydration.
So the Dai team engineered the biological lock to require a chemical key that just doesn't naturally occur on the human epidermis.
Exactly. That precise engineering matters so much. They've completely separated the operational parameters of the device from the destruction parameters of the device. The conditions required to make it work are biochemically isolated from the conditions required to make it die.
Which is everything. I mean, looking at the success of this, the synergy of the enzymes, the zero microplastic footprint, the rock-solid stability of the trigger, the immediate temptation is to view this as the ultimate silver bullet.
Oh, of course.
You read this paper and you just think, incredible, we just need to scale this up, embed these engineered spores into every single grocery bag, water bottle, and food clamshell on the planet, and we can finally clean up the oceans.
And this is precisely where we must pull back and apply a really rigorous, scientifically honest reality check.
Yeah.
Because we have to contextualize this discovery against the actual macroscopic data of global plastic pollution. If we misunderstand the scope of the problem, we will completely misinterpret the utility of the Dai team's invention.
And the numbers provided by the UN Conference on Trade and Development, the OECD, and the UN Environment Program they're just difficult to even process. Let's just trace the curve for a second.
We'll do it.
In 1950, at the dawn of the modern plastics boom, global production was around 2 million tons annually. Today, the global economy is churning out roughly 450 million tons of plastic every single year.
It's staggering. The acceleration is totally unprecedented in materials history. But the production volume is actually only half the crisis. The life cycle data is much, much darker.
How so?
Well, the UN Environment Program data shows that approximately 75% of all plastic ever produced since 1950 has already transitioned into waste. It served its brief operational purpose, and now it is simply sitting in the environment.
Man! And we've spent decades emphasizing recycling infrastructure. We put the blue bins absolutely everywhere. But the thermodynamic reality of recycling tells a totally different story. Of all that plastic waste generated over the last 70 years, only about 9% has ever been recycled.
Just 9%. And that low percentage isn't just a failure of human habit, it's a fundamental failure of physics.
Really?
Yeah. When you melt down a polymer like polyethylene to recycle it, you subject the molecular chains to immense thermal and mechanical shear. The chains physically break and they shorten.
Oh, so the material actually degrades.
Exactly. You degrade the tensile strength and the clarity of the material.
Yeah.
You physically can't recycle a plastic bottle into a new plastic bottle indefinitely. It's a downward thermal spiral. Because true, infinite recycling is so mechanically difficult, the vast majority of our plastic, that other 91% ends up incinerated, buried in landfills, or leaking directly into the biosphere.
And the volume of that leakage is the statistic that completely stops you in your tracks. The sources report that somewhere between 19 and 23 million tons of plastic waste leak into aquatic ecosystems, our oceans, rivers, and lakes every single year.
It's almost impossible to visualize.
It is, but the source equates that 23 million tons to 2,000 garbage trucks fully loaded with plastic waste. Picture standing on a coastline. Watch 2,000 garbage trucks reverse to the shoreline and dump their entire payload directly into the surf. That is happening today.
Right.
And tomorrow, another 2,000 trucks arrive, and the next day. It is an unrelenting daily avalanche of synthetic polymers entering the food web. And the economic modeling suggests that without a massive systemic intervention, global plastic production will hit over 700 million tons annually by 2040.
Yeah, the scale is terrifying.
So what does this all mean? Staring down the barrel of those numbers, we have to ask the hard question. Why does this living plastic research matter if the source material explicitly states that the Dai team's invention is not a solution to this specific ocean plastic crisis?
Well, we have to look at the chemistry of the waste stream. The Dai team engineered their biological demolition crew specifically for polycaprolactone. PCL is a brilliant material for medical implants, for 3D printing, and for specific lab applications because of its low melting point and its biocompatibility.
Okay.
but it is a very niche polymer. The 2,000 garbage trucks backing up to the ocean every day are not full of PCl. They're full of the big four: polyethylene, polypropylene, polyethylene carethylene, which we know as PT, the stuff water bottles are made of, and polystyrene.
So the chemical structure of a PET water bottle is entirely different from the PCl sensor substrate they tested.
Radically different. Polycaprolactone is an aliphatic polyester, meaning its backbone is held together by ester bonds that are relatively vulnerable to hydrolysis.
Okay, so the enzymes could actually break them.
Right, the Bacillus subtilis enzymes were specifically tailored to cleave those ester bonds. Polyethylene, on the other hand, is composed of carbon single bonds. It is one of the most stable, unreactive chemical structures we've ever mass-produced. The enzymes that beautifully deconstruct PCl would be completely useless against polyethylene. They wouldn't even recognize it as a substrate. It's like trying to use a key cut for a Honda to start a Boeing 747.
That makes so much sense. But even if we could engineer a biological crew to eat PT or polyethylene, the trigger mechanism we discussed earlier presents a massive environmental barrier, doesn't it?
Oh, absolutely. Let's say you miraculously adapt this technology for PT water bottles. Remember, the trigger requires a 50 degrees Celsius nutrient broth.
Yeah, 122 degrees Fahrenheit.
Right. The average temperature of the Pacific Ocean is around 4 degrees Celsius. It is freezing, it is saline, and it is largely devoid of the specific L-alanine amino acids required to break spore dormancy.
So if a living plastic bottle falls into the ocean, the trigger conditions are literally never met.
Never. The spores stay asleep forever, and the bottle persists for centuries, just like a normal bottle.
And beyond the chemistry and the environmental triggers, there's also the brutal reality of industrial scaling. The source points out that moving from a carefully controlled laboratory experiment to global mass production is a multi-year, often insurmountable hurdle.
Translating lab-scale biology to industrial manufacturing is notoriously difficult. Remember, the Dai team successfully embedded stores into small batches of PCl, which has a relatively low melting point of about 60 degrees Celsius.
Right, the spores can survive that easily.
But PT melts at 260 degrees Celsius. If you try to mix spores into a commercial PET extrusion machine, the thermal load will incinerate the biology instantly. You'd have to completely reinvent the manufacturing process of global plastics just to keep the sleeper agents alive during fabrication.
Okay, so it doesn't solve the ocean crisis, it only works on a niche polymer, the trigger doesn't work in seawater, and it's incredibly difficult to scale to other plastics.
That's the reality.
If I am a skeptic, I'm looking at this and asking, why are we dedicating an entire deep dive to it? What is the actual tangible value of what the Dai team has accomplished if it doesn't stop the garbage trucks?
I get that perspective. But the value lies in the architecture of the solution. You see, science rarely delivers a monolithic cure for a global crisis in a single paper. What the Dai team has delivered is a profound, undeniable proof of concept.
Okay, go on.
They have fundamentally proven that the physics and biology of internal programmed molecular disassembly actually work. They've demonstrated that you can successfully embed dormant biological agents into a polymer matrix, maintain their viability, and use an active command to flawlessly execute complete degradation without generating microplastics.
So it is the architectural blueprint.
Precisely. The specific enzymes will change and the specific polymer will change. But the methodology, the concept of the biological Trojan horse, is a revolutionary new tool. It opens an entirely new door in materials science. We now know the mechanics of active command degradation are actually possible.
And if we acknowledge that this isn't meant for bulk packaging or replacing the billions of polyethylene bags used globally, it forces us to look at where this technology actually belongs today. And that inquiry leads us directly into a rapidly expanding, highly specialized field of engineering that has been quietly operating right under our noses. We're entering the world of transient electronics.
Yes, transient electronics represents a fascinating inversion of traditional engineering principles. For decades, the primary directive of electrical engineering has been robustness. We design circuits to withstand thermal cycling, moisture, and mechanical shock. We want devices to last.
But transient electronics is an entire subfield dedicated to devices that are explicitly designed to die.
Exactly. It exists at the bleeding-edge intersection of materials science, bioelectronics, and highly specialized device engineering.
And the source material notes this field has been quietly growing for over a decade. Researchers have been obsessively pursuing the holy grail of on-demand programmable destruction. But the Dai team's living plastic isn't the first attempt at this. Before they managed to embed dormant spores, How are engineers trying to make hardware self-destruct?
Well, the early methodologies were highly inventive, but they often lacked precision. The source details several approaches. One method relies on heat-triggered structural collapse.
How does that work?
Engineers utilize polymers with very specific low glass transition temperatures as the substrate. When the device receives a signal, an internal resistor surges heat. The polymer instantly loses its structural integrity, and the device basically just warps and melts.
But that doesn't actually degrade the material, right? It just ruins the circuit.
Exactly. It destroys the function, but the mass remains. Another much more aggressive method involves chemically produced bubbles.
Bubbles.
Yeah. Engineers embed microcapsules of reactive chemical, often solid acids and bases, into the device casing. When triggered by heat or a specific electrical pulse, the microcapsules melt, the chemicals mix, and they rapidly produce microscopic bubbles of carbon dioxide gas. The sudden internal pressure physically tears the device apart from the inside.
Oh, wow. That is basically a microscopic explosive charge. It shatters the device, but again, you're left with a debris field of tiny electronic and plastic fragments. It solves the security problem of destroying the data, but it completely ignores the environmental problem.
Right. And then there are methods using passive enzyme-degradable polymers. These are plastics engineered to be susceptible to enzymes naturally found in the soil or the human body.
But those lack the control of the Day-Team's active command trigger. If it relies on environmental enzymes, it starts slowly rotting the moment it hits the soil or the bloodstream. You can't control the timeline. So why is the demand for transient devices growing so rapidly? Who actually needs a device that vanishes?
The applications are highly specialized and incredibly high value. Let's examine the medical field first, where the stakes are obviously highest. Consider the bioresorbable vascular scaffold, basically a temporary stent.
Okay.
When a patient has a blocked artery, a surgeon inserts a stent to hold the vessel open while it heals. Traditional metal stents remain in the body forever, which often causes long-term complications or requires a second, highly invasive surgery to remove them.
Right.
But a transient stent acts as a robust mechanical scaffold for the necessary 6 months, and then, triggered by the body's specific internal chemistry, it simply dissolves into harmless lactic acid that the body naturally metabolizes.
Wow. Or consider neural electrodes. If a patient requires short-term monitoring for, say, epileptic foci, surgeons place arrays of electrodes directly on the brain. Leaving foreign wires in the cortex long-term invites infection and glial scarring. But extracting them requires a second craniotomy. Imagine an electrocorticography array built on a transient substrate. It provides flawless, high-resolution neural data for 4 weeks. Then, upon receiving a targeted ultrasonic pulse or a specific chemical trigger, the substrate liquefies and the microscopic conductive traces safely disperse and are flushed from the cerebrospinal fluid.
The elimination of extraction surgeries fundamentally alters the risk calculus of internal medicine. But the environmental applications are equally transformative.
Oh, yeah, agriculture, right.
Yes, look at modern precision agriculture. To optimize yield and minimize chemical runoff, megafarms increasingly rely on distributed environmental sensors to monitor soil moisture, pH, and nitrogen levels.
Okay.
Currently, deploying thousands of plastic and silicon sensors across thousands of acres creates a massive retrieval problem. When the harvest is done, you either spend an exorbitant amount of labor manually retrieving every single sensor, or you abandon them, slowly accumulating electronic and plastic waste in the topsoil generation after generation.
Here's where it gets really interesting. A transient sensor flips the economics and the environmental impact completely.
Completely.
It's like the iconic mission. Impossible self-destructing tape, but applied to medicine and agriculture. You deploy a swarm of transient sensors. They monitor the soil telemetry for the entire growing season, communicating data back via passive radio frequency. Then, when the season ends, a specific trigger, perhaps a targeted chemical spray deployed with the final post-harvest treatment, activates the dormant demolition crew. The sensors melt into biologically benign monomers right there in the dirt.
Zero retrieval cost, zero accumulated waste.
The source also touches on secure communications devices, hardware that physically vanishes to protect sensitive data and wearable medical patches that degrade upon disposal, keeping contaminated biological waste out of the complex, high-temperature incineration streams required for medical refuse.
If we connect this to the bigger picture, you realize all these applications are trying to solve the same fundamental engineering paradox. I refer to it as the timing problem.
The timing problem. Let's unpack the mechanics of that.
The timing problem is the conflict between operational reliability and end-of-life rapid disposal. If you use passive, biodegradable plastic materials that rely on environmental moisture and microbes to break down. You are dealing with a slow, linear decay curve. The material begins rotting from day one.
Oh, I see.
You can try to formulate it to last longer, but you are fundamentally working with a compromised structure. Its reliability is constantly degrading.
You definitely don't want your neural electrodes slowly rotting while you're still relying on its data.
Exactly. The Day team's living plastic fundamentally solves the timing problem. By sequestering the biological demolition crew in a dormant state and requiring a highly specific active command to wake them up, they have changed the decay curve from a slow, linear decline to a sharp step function.
Right.
The device operates at 100% structural and electrical integrity for its entire useful life. It does not rot, it does not weaken.
Yeah.
But the absolute second you initiate the trigger sequence, it drops rapidly and relentlessly to zero. It gives the engineer unprecedented control over the timeline of destruction.
That distinction, the shift from slow, passive rot to active, commanded destruction, it changes our fundamental relationship with the physical objects we build. We are no longer just agonizing over how a device functions during its operational life. We are actively engineering the precise mechanics of its death.
It's profound.
It is, which moves this conversation away from the microscopic actions of endoenzymes and into the broader philosophical implications of material science. We are standing at the threshold of redefining the very concept of durability.
We are witnessing the elevation of life cycle programming from an afterthought to a primary engineering parameter. Historically, a mechanical engineer designing a component would sit down and dictate the required tensile strength, the thermal resistance, the electrical conductivity. Durability was essentially treated as an inherent property of the chosen material.
Right. If you chose plastic, you accepted its permanence as a structural reality, something you either desired or simply had to work around.
But now, lifespan is becoming a tunable dial on the dashboard. An engineer can say, I need this to bear 20 pounds of force, I need it to conduct electricity, and I need it to cease existing in exactly 6 weeks.
It is a radical expansion of the designer's toolkit. However, the source material is careful to establish the current boundaries of this paradigm shift. We must reiterate what does not change, at least not yet.
That's an important caveat.
Right. This targeted impermanence is not currently viable for the microscopic structural world. The steel and high-density polymers in our architecture, the composite plastics in our vehicles, the vast quantities of polyester fibers woven into global textiles, these require entirely different massive-scale industrial solutions. We are not going to see transient skyscrapers, and we aren't going to have t-shirts that dissolve if we accidentally wash them at 50 degrees Celsius.
No. But the momentum in the specialized sectors is accelerating exponentially. The source highlights that this research is highly distributed. It's not just the Dai team working in isolation. Because the underlying logic of the biological Trojan horse is so sound, hundreds of labs globally are tackling different facets of the problem.
Oh, wow.
Yeah, the Dai team is already attempting to modify the germination receptors of the Bacillus subtilis spores to respond to water triggers rather than 50-degree heat, specifically targeting marine environments.
Wait, really? If they can genetically alter the spore to wake up in 4-degree salt water, then suddenly that niche polycaprolactone technology begins to have real implications for oceanic sensors and marine equipment.
Exactly. Simultaneously, other biochemical teams are searching for the right enzyme pairs, the lumberjack and the wood chipper, for the massive bulk polymers. They're studying organisms like Ideonella saikiensis, which is the bacteria discovered in Japan that can actually degrade PET plastic. They're trying to isolate those enzymes and figure out how to encapsulate them or program them into spore-forming carriers that can survive the 260-degree thermal extrusion of commercial plastic bottles.
It is a quiet, highly coordinated revolution happening in bioengineering labs all over the planet. And understanding the trajectory of this research really forces you to reevaluate your immediate physical surroundings. I want you, the listener, to just pause and look around the room you're sitting in right now. Look at your desk, the electronics, the packaging in your kitchen. Almost every synthetic object we interact with is built on a massive, unexamined design flaw, the assumption of infinite material persistence. We manufacture a rigid plastic clamshell to protect a salad for the 10 minutes it takes to transport it from the deli to our desk. The operational lifespan of that object is 10 minutes, but the physical lifespan of the polyethylene it is made from is 400 years.
It's an absurd, almost comical mismatch between the utility of the object and the durability of its atomic bonds.
Right.
And this raises an important question. That mismatch is the root of the global waste crisis. The source captures this philosophical pivot beautifully, noting, What changes is the conversation about what we leave behind.
Yes.
For the entirety of the plastic age, we viewed the permanence of our waste as an inescapable curse of chemistry. We thought durability was a static law of nature for synthetic polymers. But the collective output of this new field suggests that durability is just a parameter. It's a setting we have been blindly leaving on maximum. Now, armed with engineered biology, we are finally learning how to turn the dial down.
The source refers to this as an honest hope. It is a narrow hope today. We know these engineered spores won't magically consume the Great Pacific Garbage Patch tomorrow, but it is a hope that is grounded in hard, undeniable mechanics. We are witnessing the birth of a new lineage of materials, beginning in surgical suites, in high-tech agricultural fields, and in classified server rooms that are fundamentally designed with their own ending written into their code.
It's the evolution from designing static artifacts to designing complete closed-loop temporal processes.
Let's pull the massive scope of this journey together. We started by examining a deceptive, ordinary-looking piece of plastic and uncovered the biological demolition crew locked inside it. We broke down the vital mechanical synergy between strain 1, the endoenzyme lumberjack that randomly shatters the polymer backbone, and strain 2, the process of exoenzyme wood chipper that meticulously dismantles the fragments into single monomers, guaranteeing a zero microplastic footprint.
We analyzed the brilliant multi-factor trigger system, explaining how extreme spore dormancy is maintained until the precise combination of physical surface erosion and a 50°C nutrient heat shock safely unlocks a biological payload, resulting in total degradation in just 6 days.
We confronted the brutal statistics of the global plastic crisis, the 450 million tons produced annually, the sheer physical reality of 2,000 garbage trucks leaking into our waterways every day, and we rigorously explored why this specific polycaprolactone technology, while not the immediate cure for oceanic PE, serves as the critical, undeniable proof of concept for internal program disassembly.
And we mapped the frontiers of transient electronics, moving from chemical bubbles to active command biological substrates, proving that in medicine and agriculture, solving the timing problem allows us to build robust devices that perform flawlessly before cleanly erasing themselves from the environment.
We have covered a tremendous amount of biochemical and engineering ground today. But as we wrap up this deep dive, I want to step back from the enzymes and the polymer chains and look at what this all means for us as a species.
The closing sentiment of the source material offers a profound philosophical challenge, and I really want you to spend some time turning this over in your mind. If you look at the broad sweep of human history, our engineering has essentially been one long, desperate war against decay. We have spent millennia trying to outsmart entropy. We forged metals that wouldn't rust, we poured concrete that wouldn't crumble, and we synthesized plastics that would never rot. We have always defined our technological success by how long our creations could outlive us. But what happens to our society, to our environmental footprint, and to our understanding of our own legacy when we finally embrace impermanence as a virtue? Look at the synthetic objects surrounding you right now. The ultimate mark of our technological maturity in the 21st century might not be our ability to forge monuments that last forever. The ultimate achievement might be, as the text so perfectly states, finally having the wisdom and the engineering capability to allow the things we make to belong to time.
To belong to time. That is a truly profound perspective to end on. Thank you so much for joining us on this incredibly detailed deep dive today. Keep questioning the mechanics of the world around you. Keep looking closely at the ordinary things, and we will see you on the next deep dive.